Friends, this is Kumar Physics. Today I am going to discuss about the interference. Interference. So that interference can be defined as, for the formation of interference, let us consider two sources, y1 equal to a1 sin omega t and y2 equal to a1 sin omega t plus delta. Okay, so to get the resultant from the principle of superposition, the resultant displacement is equal to sum of the individual displacements. So if they are having the different amplitudes and nearly same frequency and maintaining a constant phase difference, then it is said to be constructive interference. That means like this. If these waves are moving like this, then you will get constructive interference like this, which will get the bright image. So to get the dark, then the wave is like this, then the output is like this, so you will get the dark image. Okay, now to get the resultant amplitude, then apply the parallelogram law factors a1 square plus a2 square plus 2a1 a2 cos phi. Now the amplitude is same, so a1 square plus a2 square nothing but a1 square plus 2a1 square cos phi. Now a1 square common plus 2 1 cos phi. 2a1 square multiplied with 2 cos square phi by 2. So the resultant amplitude square, this is the resultant intensity. So 2 multiplied with 2 square, this is initial intensity, cos square phi by 2. So the resultant amplitude is 4a0 cos square phi by 2. 4a0 cos square phi by 2. For getting intensity maximum, the phi should be up to under 2n pi, where n equal to 0, 1, 2 and so on. Then the path difference is represented by delta x. This is called what? Phase difference. Phase difference. And this is called what? Path difference. The path difference is nothing but n lambda. Remember, for lambda you will get phase difference as 2 pi. So instead of 2 pi you can write lambda. Now for I minimum, nothing but destructive interference, we will get dark image or dark fringe. So that phi should be 2n minus 1 multiplied with pi, n starts with 1, 2, 3 and so on. Okay, so the phase difference is that one, and the path difference is 2n minus 1 into lambda by 2. 2n minus 1 into lambda by 2. So like that, this is the condition for maximum and minimum in the case of interference pattern. So to explain the wave formation, how the bright fringes are observed and how the dark fringes are observed. Now this is an Young's double slit experiment. Young's double slit experiment. This is called what? YDSE. YDSE. So now let us consider a primary source. That primary source is emitting the waves in the form of crust and troughs. Okay. Now these crust and troughs will pass through two slits S1 and S2. S1 and S2. So you will get like this. Okay. Again from this also you will get like this. Now draw like this, and these are coincide. For constructive interference, the crest of the first wave and crest of the second wave coincide, or the trough of the first wave, trough of the second wave coincide. Then represent like this dot. For destructive interference, crest of the first wave and trough of the second wave is coincide, or reverse, and trough of the first wave and crest of the second wave combined. Then represent with circle. Okay. Now see here. This is the crest of the first wave. This is the crest of the second wave. So you will get dot. Here also dot. So with the help of these two, you will get the bright fringe. That is called the central maxima. Central maxima. If the waves goes on increasing, that means see here, this is the minima and this is the minima. By joining this, you will get the first dark. Okay. If you join like this, you will also get the first dark here. Like that, you will get the image as, you see the first central maxima, next first dark on both sides, next first bright on both sides. Like that the images will come. Okay. That is about the explanation of Young's double slit experiment. Now go to diffraction. In diffraction there are 2 points. What is meant by diffraction is bending of light. Bending of light at the edges of obstacle. And this of obstacle for the encroachment of light. So there are two scientists who observed this one. First one Fresnel and second one Fraunhofer. Fresnel and Fraunhofer. According to Fresnel, the distance between slit and screen, that is source and screen is finite. Okay, finite. And second point, no lenses are required to see the image, to see the diffraction pattern. Third one, the wavefronts used as spherical or cylindrical. That means when the source is here, then the light waves which are coming from this point will be emitted like this, spherical waves, and they are passed through the slit S1, and they will be emitted like this, and these are incident on the screen. That means the distance between this slit and screen, source and screen, is finite. That is about the Fresnel. That way the Fresnel distance is represented by a square by lambda, where a is called the size of obstacle, size of the object. Okay. Next, Fraunhofer diffraction. Fraunhofer diffraction, here instead of finite they are using infinite. Instead of finite they are using infinite, first one. Second point is no lenses, means instead of no lenses they are using the lenses. Use of lens is important. Third point, plane wavefronts are used. Because the long distance communication takes place, that's why spherical is converted into plane. So that's why they are sending like this. The light wave which is coming from the plane and incident on the slit, then they will pass through the and incident on the surface of a lens, which will produce like this, the image which is catched on the screen. These are at infinite distance. Source and screen are at infinite distance. Okay.